So random fun part for the day is I'm going to attempt to video some of your discussions today. It's not really because like it's nothing about you guys, it's about me. I'm applying for my national boards, which basically tells the state of North Carolina and the nation that I'm a pretty dang good teacher. So I have to prove it to them with lots of essays and videos, and I have to take a really big test in May, so cross your fingers for me. So basically I'm just going to stress myself out just a little bit more. But don't worry at all. Basically be your normal awkward selves. That's all I need. When we get into our group conversations, no changes at all to normalcy. It's just whenever I am, actually one of my lab assistants are going to be videoing, and it'll be about 10-minute snapshots because I can only submit like a 10 or 15-minute video. So you may be in it, you may not, but eventually I'll give you a signature page to basically sign your face away. Okay. Say again? I'll just make sure that I capture some of your conversations, that's all.
I want to be famous.
You might be famous. Actually, only people who grade me will see this, but we'll remember that. Okay. So I'm going to scroll back to the top and let's talk about this, okay? So we talked about bond polarity, and now we're talking about molecular polarity. So I want you to draw on your paper a bond. Just draw a bond. What are you drawing? What are you drawing? A line, okay. There's our bond, and I want you to make it seem as if it's a polar bond. What are you going to draw on it? The dipole thing, right? Yeah. So I'm just going to make an atom and an atom, so A and B. And then I'm going to draw, let's say atom B is more electronegative, so it goes towards atom B. The arrow, okay? Perfect. All right, so now if I'm looking at a molecule, I can see that, this molecule is AB. I can draw a whole other molecule. Let's say I draw A, B, A, okay, and they're connected with these bonds. Well, the AB bond is polar, right? So the bond is polar. So if I draw that on a molecule, I draw the arrow towards B again, and towards B again. So when I draw that arrow, the arrow is supposed to be representing a partial negative or a partial positive. Which one? Why negative, CJ? Right, so the electronegativity is high on that part, that B atom, so it's pulling electrons towards it, which gives it a partial negative charge. So you have to, I'm just going to kind of draw this across the whole top. This whole region up here is partial negative. So if I'm pushing electrons from A to B, I'm pushing electrons from A to B, what kind of charge is left on A? Why partial positive? Right, so the electrons are shifted up a little bit, so this is leaving it with a slight positive area and a slight positive area. So then down here, you have a partial positive and a partial positive. So when you're looking at this molecule, you see a partial positive on the southern region and you see a partial negative on the northern region. Would you say that this is an equal or an unequal distribution of charge? Why unequal, Hannah?
Because there's two partial positives and also partial negatives.
Right, and just the mere fact that there are lots of, there's one whole area that's positive and one whole area that's negative, it's definitely not equally distributed in any way or form. So if it's an unequal distribution on the molecule, would you consider that a polar molecule or a non-polar molecule?
Polar.
Jacob? Why polar?
Because there's a difference in electrons.
Well, not just electronegativity, but just electronegativity, the shape, and that causes a whole unequal distribution of charge. So, what we were talking about 2 days ago and yesterday a little bit was that bond. Is it polar, non-polar, or ionic? And now we're thinking about, okay, how does the shape and those bonds play into the whole molecule? And now we're calling out molecules polarity, which is just, it takes maybe 2 or 3 moments to think about it, but it's talking now about the entire molecule's entity and how the charge is distributed. You have to be able to visualize this and have some spatial reasoning, but that's where we're building the molecules, because you can say, okay, this side is partial positive, this side is partial negative, or vice versa, and it's going to be considered polar. So we're looking for an area partial positive and partial negative, and what that basically means is that it's magnetic. It would respond to a magnetic field. That's just kind of application. And like we just did with that exercise, we looked at the bond polarity and the shape. So with the bond polarity, I put a little asterisk here because there's a consideration. If it's nonpolar NPC, you guys know that means nonpolar covalent. Okay, if it's nonpolar, if the bonds are nonpolar covalent, generally, like A to to B, there would be no dipole moment. There's no partial negatives, no partial positives, so it's just nonpolar. The molecule itself is nonpolar because there's no weird charge comparison here. So that's generally the rule. You might find some instances where that does not exactly follow. And if it's polar, you can't just say, hey, it's polar bond, it's polar molecule. You have to consider how shape plays into it. So if you have a polar molecule like this, a polar bond like this, A to B, and A to B, let's call out B again, it's the more electronegative one. How do the dipoles point on this bond? Say again? Towards B, right? So I'm going to point this arrow towards B. And again, A to B, B is more electronegative. How do I point this arrow? Towards B. Okay. So stand up for me. I need 3 of you to stand together. Yeah, most of you can stand up. You can stand up for me. 3 of you stand together. Or 3 people stand together. All right, so stand up here. Okay, so Ryan's going to be A, and then these 2 guys will be B's. Okay, hold your arms out. All right, and so B's are electronegative, right? You're going to have to touch. Okay, you're going to have to touch. So now grab his wrist, and so basically there's 2 electrons being shared here, but they're pulling, the B's are going to pull the electrons out, not so you don't pull his arms out, guys. Pull the electrons out. I guess pulling the electrons out. Okay, so they're trying to pull the electrons to the other side, but neither of them are going to win this tug of war because they're pulling those at the same strength. So what happens is it cancels out. It nullifies the pull. It nullifies the dipole moments. And so is this whole molecule polar or non-polar? Non-polar. Good. Okay, drop. Go back to your seats. Let's turn the laptop on. So what shape were they representing up here? A line. So what's that shape? It's a line. Linear. So for this particular shape being linear, that linear geometry, that linear shape allowed for the cancellation of those dipoles. There was a straight line, left and right, equal poles, it canceled each other out. So that's how geometry plays into it. So overall, that particular example we just did was nonpolar. The example, I'll scroll right back down here. This one up here, if they had been in a bent shape, and in that bent shape, if they had been pulling down to the bottom, the bent shape's not allowing for those cancellations to occur, so that's why it would yield a polar molecule still. So the shape has a lot to do with if in the end we call it a polar molecule or a non-polar molecule. And I see confused faces still. Who feels like they have it like halfway? Like you can maybe determine polarity halfway. Okay, I'm okay with that because you guys are in your lab be conversing about this to really get a hang of it. And there's an example here, which does anybody recognize this molecule? Does anybody recognize this molecule? H2O, great, that's water. We all probably recognize water as polar, maybe just from biology because they told you, oh, it's a polar solvent. But it's polar because this is hydrogen and oxygen, and the hydrogen and oxygen comparison, electronegativity is quite high on oxygen. We push electrons towards it, and what gives oxygen octet in this Lewis dot structure? What's on here? It's not listed, but it should be here. 2 lone pair, right? There's a huge lone pair there, there's a huge lone pair there. Well, they're super duper duper negative, so that's a huge partial negative here. The hydrogen pushing its electrons towards oxygen leaves us with a huge partial positive here. So on the left side, it's partial negative. On the right side, it's partial positive. Equal or unequal distribution of charge. Unequal means polar. Equal means nonpolar. Unequal means polar. So that's why water's polar. And then my favorite, help, I'm dissolving. But wait, bears are insoluble. It's easy for you to say, you're not polar. Because he's a polar bear. Okay. But it's also because polar dissolves in polar solvents. Okay. All right, so on our lab sheet, which ones were the most difficult ones? I'll maybe do one before we get up and go. Say again? XC F4, that one? Oh, OF? Okay. So with this one, who can tell me, okay, first off, how many electrons do we have? 42. Okay, who's the central? Okay, we have two singletons, right? Xenon and oxygen. How do you, once you get like, okay, carbon's our preferred one, we have no carbon. So then you go to singleton, xenon, oxygen. All right, so we don't know who to choose. What's our next priority? Biggest. So who's the biggest in terms of atomic radius? Xenon, right? Xenon's way bigger than oxygen. So xenon will be in the middle, and then everything else gets connected. Fluorine's just as symmetrical as I can get them, and an oxygen. Okay? So we went valence electron, skeleton, E. What's E? So add electrons until what? You reach octet. So 2, 4, 6, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. Okay? Everybody has the 6 plus the bond, so they have octet. Xenon, has what? 10. Why is that okay?
It's one of the special ones.
Special one, I can expand octet, so it's totally fine. And if I count this up, I have 8, count with me, 16, 24, 32, 40, but I have 2 more, so what do I do with those 2 extras? Put them on the middle. And so I can see that really well. If you could just circle those for me, it would be helpful for when I'm looking over this. And so from there, you can't get the shape from this structure. You have to build it, and then we'll talk about what the shape looks like. Some of these are going to be visualization exercises. Okay? All right, the rest of the questions I'll answer in your lab groups once we get there. So what you guys are going to do is you're going to build, and probably maybe 3 or 4 at a time, and I'm going to check them as I can, because there's a lot of you, and I'm slow, and I'm going to come around and check your structures, talk about polarity and so forth. Each hole, like on the middle central bead, should be filled either with a bond or it can be left open to represent the lone pair. Don't put those little teeny tiny white things in there because they are so hard to get out, right? I tried that yesterday. It's not fun. If you have a single bond, use the short stubby ones. If you have a double or triple, use those flexible ones. And then don't throw them and lose them. I just found a piece for my last class, so put this back in the box. Try to make sure things go back in the boxes they came from. Got it? All right, so just be patient with me. You can get ahead, but just understand I got to check a couple at a time. So I will check off on your papers whenever I've seen it, and we're good. So let's work in groups of 2. Grab a kit and disperse. Okay? Groups of 2.
If there's any
Alright, please find a place to sit or stand or whatever. In 10, 9, 8, 7, your place. 5, your place where you are. 4, 3, 2, 1. Okay, so let's know where you started. Have a moment of comparison. Stop, that's for a minute. Have a moment of comparison between all your loose dot structures. Before you start building, compare your loose dot structures with each other so you know you're good. Oh, sorry, banana. Grab a different kid. That's the example printer. That's the big one. It's not just a more complicated thing to make. Carmen, it's black.
Okay, I'm not going to keep first.
That's what's up for you, okay? 3, 2, 1. So I see you guys are doing a great job with starting to build. Listen up. But the goal here now is for you to complete the rest of the chart. So you are going to be able to do molecular polarity. Because you're going to start to think, okay, how are the electrons arranged in terms of the dipoles and in terms of polar and nonpolar. You also should go look at how many electrons in the central atom. The only column you don't have any information on is the last column you see I have. Because you're waiting there. But like I said, get 2, 3, 4 built. Discuss with your partner's polarity. What you should be able to do is to like really describe and justify why you're calling from your polar and nonpolar. Don't just say, oh, the answer is polar. Like really so you want to get these fast. All right, so keep rolling.
How does the Lord
Yeah, so negative
Oh, yeah.
It doesn't have to be yeah, it doesn't have to be. Yeah, it doesn't matter. I like the okay, so H2SE. Yeah, I just that makes a lot of sense. Okay, so high school SE would be on. This is not fully. It's the actual thing.
Now
So this would mean nothing but meaning. That would be. Yeah, but the electrons that's also going to be because it has the same polarity. Yeah, that's what I'm saying. No, it's nothing. Because it's all negative. Yeah. Let's move on to that. That's what I said, not right. Yeah. Okay, so what if you don't see it? Like this. So where we, where's here's the range. Oh, the polar not on. Okay. So non-polar, but there's Oh, you got like a double bond. No one cares if you're shaking. Alright, so it's all the polar non-polar. Because there's no variation in the charge. I saw this hand on there. That makes sense. Yeah. You did. Alright, Wait, why is there one? Oh, there isn't. I just saw the video. And so that was right. So these and now the other one is all yeah, sure, yeah. Alright, so that's I'll get this. Alright, okay, so what's the stick for F? So what's 4 These are all negatives. So it's xenon yeah. I mean, it's still like, I was saying that even if we Class 3, 2, 1. Somebody may have already built this. Hold up PCL 5 and you have it built. PCL 5 is like the third to last one. Okay, if you don't have it built, it's okay. Look up here for me, okay? So if you hold it so that you have 3 in the middle on the equator and 2 on top and bottom, you should be able to see the structure. You don't even have to look at your paper. So if I have a triangle in the middle, because there's 3 in the middle, and I have kind of a pyramid on top and a pyramid on bottom, what would we call that? So it's a pyramid on top and a pyramid on bottom. Well, you remember, we're not fancy with our words in chemistry, right? So it's a what in the middle? Triangle. So again, here it is. Trigonal to the trigonal, and there's 2 pyramids right in the middle. Told you we're not fancy here, so it's little. It's very much what you see.
I thought I saw it and I didn't go get it. Yeah, we got I don't understand what the loan is. I thought loan here was all great. That's what I
Are you guys should be wrapping up probably in the next 10 minutes? You still need to build all of the structures.
That would be. Why can't we just all use like that?
M2 is non-polar. If it's
Alright, listen up for me. 3, 2, 1. Who has built Xenon with the O and X4? Okay, so hold it up like this if you have it. You take the lone pair off because the lone pair is kind of distracting sometimes, because sometimes you write in it. So if I hold it like this, you see the green stuff, it kind of makes a right shape. A square, okay? And then the red up top, if you look at it, it makes a pyramid, right? So what's the shape? Square pyramidal. Now, before I move from here, we have this big lone pair, right? Huge lone pair on the bottom. Super, super wet charge. Negative, okay? Then you've got some partial work on the chlorines. So you've got, was it xenon chlorine? Who's more likely negative, xenon or chlorine? Chlorine, okay, so we have a partial negative here, 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 here. But that can't compete with this partial negative, the lone pair case. So that's two huge lone, or negatives which are coming from lone pair. Then you have oxygen, xenon or oxygen. Oxygen is kind of electronegative, right? It's not as electronegative as chlorine. So I know this is a weird one. You have partial negatives actually all the way around, but are they the same? Are they the same partial negatives? Yes or no? No, because the lone pair and the oxygen are very different. So we call this equal or unequal. Unequal, therefore, polar. Okay, and it's because there's no symmetry for the
Is that a
I think so, but then I don't think so. I'm like, I get it, and then I don't get it. And you have to talk to the yeah. It doesn't make sense.
So like,
And help with the other thing.
all right, 5 minutes to get this polarity figured out. Alright, group one more time. After me, 3, 2, 1. Good build, XEL4. Raise your hand. XEL4, I think it was the fourth one. A couple of us, can you hold it up? I see some incorrect structures, because what else is on the xenon? How many of them here? How many? 2. Okay, so we have this group, we're gonna hold theirs up, okay? So this is not a tetrahedral structure. The tetrahedral doesn't have any living pairs, right? Okay, so can you guys think about maybe name that for me? What kind of shape do you see? A square, and is it a pyramid? So what's another name for flat square? Well, square, planar. Those are the only 2 words. Planar or pyramidal, right? We're not fancy. So it's a square and it's a flat square, so it's square planar. So what's on top and bottom here? So we have a lone pair on top, hugely negative. We have a lone pair on bottom, hugely negative. Okay, what do you think those partial negatives and partial negatives are going to do? Cancel each other out, so those don't really matter to us anymore. And these are what, fluorines? Okay, so we have some symmetry on this here. So all the fluorines are electronegative, pulling electrons out, 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 out. So what we call this, polar, nonpolar. Why nonpolar? It's equal everywhere, it cancels each other out. There's no bend structure to it, no pyramidal structure. You can rebuild that so you can see that in your table.
I can tell when I'm being
What if what if more than one element? I'll get it. Not even anything. Are you done? You guys go back to your desk and good luck to the second
Bailey, you forgot a shoe.
Grab your laptop, guys.
We turn this in?
That's 8.
And all the way across.
I'll pull it up here too so you actually can see what's going on. Alright, so just look up here while you're getting logged on. The computer's take a moment. I heard a lot of really good conversation. Who feels like they're leaning now towards masters of polarity? Like you can look at a structure and you can say, okay, the electrons have been shifted this way, and I can tell if it's polar or non-polar. Like if you're over 50% now. I felt like more of you were getting that way, and some of you guys are just not participating in my survey for some reason. So when I quiz you, I'll know for sure if you're a polarity master or not. But basically that piece is it's kind of challenging, but once you get it, you got it, and you can apply it to everything next. So why this matters right now is once you know if something's polar or non-polar, you know every physical property it could have, which is what we're talking about Monday. Okay, so if you can't get the polarity part, you'll never be able to tell, like we talk about high boiling points, low melting points, if it's volatile, if it's going to be soluble in water. So there's a lot of things that play off that. So if you don't have it yet, come to tutoring, ask somebody to sit with you, and we'll talk about it, okay? So on chapter 7, 8, with it is a combined problem set, a lot of vocabulary stuff first, so I'm going to scroll past that because I'm not using my time for that one, okay? And then it says, on a separate sheet, make a table, A through E columns, and then these 10 rows. Determine what type of bond is formed, so what are the types of bonds we have? Ionic or covalent, okay? Draw the appropriate dot structure, dots. If the compound is covalent, predict the shape and the molecular polarity. And then you won't be able to do D yet, which is IMF, intermolecular force. So you should be able to get A through C done for all of these. I would go ahead and start that table now because that is the beast of this problem set. And that is actually most of this problem set. I'm scroll down just a little bit more to let you see the rest of it, which is just basically modifying electron configurations from the elemental ground state to the ion. And I think that's probably second nature to some of you guys at this point, like talking about exchanging electrons. So I'm going to leave this middle part up because I think now you got 20, I'll give you about 15 minutes, and let's see how far we can get there. You need a ruler, feel free to grab.
Is that like, have to be on a separate sheet, or can we do it on
Yeah, basically, some people will print this out and they'll just do the matching, but it just needs to do it so I can tell what's going on.
So the table is on the board, and I suggest you turn the table right now. The table is on the board. What you should be working on the board.
I'll do the matching part later, just because it's what you need. And I know that you will need your electronegativity sheet, so if I know you took a picture on your phone, you can use that, unless you just don't want to use your battery. There's the extra sheets off the piece up on my desk, so you guys have access to the extra sheets if you need it, okay?